Just a recap of what we have done so far before we carry on. We covered a number of topics. We discussed linear systems and their mathematical representations in differential equations. We also discussed Laplace transforms and how to use Laplace transforms to find transfer functions from differential equations that define the relationship between the input and output of a dynamic system in frequency domain. We also use Laplace transforms to find the time domain responses of a system so that we don't have to solve differential equations. And then we discussed first order and second order systems, their typical parameters like DC gain, time constant, corner frequency for first order, the gain, the natural frequency, the damping ratio for second order systems. And I emphasize that we always try to get, when you get a transfer function for first order or second order system, we try to reformat it into standard formats if they are not already in that. From the responses, we also studied the issue of stability, and that leads us to the new definition of zeros and poles of a system, and how you can determine if a system is stable or not from their position of the poles, but also how fast or how slow a system may be, again, from the location of the poles. So that's what we covered so far. So the next, what I'm going to do is to carry on, and we're now being in a position to look at the closed loop control systems. And previously, we've been really sort of focused on the analysis of a system and their properties and their responses. But now we're going to move on and discuss more really the topic that we're trying to cover, that is a closed loop. Okay, so there are a number of things we're going to look at as I listed here. Now, before we do that, we need to first of all have a look of the difference between the open loop and a closed loop. Now, open loop is a system where there is no feedback, like the one block diagram on the top of this slide as you show here. So you have an input. If you supply input to the system, you get an output. There is no feedback measurement at all. There is no control either, because we don't have feedback, therefore we can't have control. The diagram at the bottom shows a typical or the simplest structure of a closed loop control. Here we have the plant, which is the object for your control. Then you take the output, you measure that, feed that through a sensor. That is fed into a comparator that compares with the input requirement. The difference between the two is fed to the controller. The controller is really the brain here. It takes action according to what error you get, and then feed the action into the plant, so that plant will respond accordingly. That's really the point of a feedback control. Now, obviously, because there's two open loop and a closed loop are vastly different, and their properties also change. So we will need to learn how a system like that in a closed loop changes the behavior and also changes the parameters of a system overall. So I will do that, but we will need to make some definitions before we try to find the closed loop transfer function. Okay. Now, over here, I actually put a lot of names onto the block diagrams. Okay, let's say ys is the output of the plant, and RS is the input of the plant, and GS is the transfer function. HS is the transfer function of the sensor. K is the transfer function of the controller. Now, input to the controller is the control error. That is the difference between the input or the overall input and the measured output from the sensor, MS. The output of the controller is US. Now, that output from the controller is fed to the transfer function of the plant, which is obviously the input of the plant. So we have a set of variables here indicating external and internal signals. And then we have 3 blocks represent 3 different systems or subsystems. The plant, the object of our control. The K, that's our controller. The HS is the dynamics of the sensor. Okay, now where HS equals to 1, then MS equals to YS, which gives us a even simpler system known as the unit feedback system. But also, if you look at any signal or any signals between any 2 signals, say from between input R and Y output, if you follow the direction of arrows, so from RS, follow the direction of arrows into the summing block, into the K, into the GS until you get to the output. This entire path is known as the forward path for these 2 signals. I could have a different forward path, for example, between E and YS. Okay, if I follow the path, then I will have go through K, go through GS until you get to YS. Or I can have look these 2 signals. I have RS and ES. So between these 2, there's really no blocks in between, so that's just fed into there. Now, for any forward path, we have forward path transfer function. That is where you multiply every block in the forward path. So between R and YS, you will have, if you look at that forward path, goes through K, goes through G, so the forward path transfer function is K times G. However, if you look at between RS and ES, there's no block there. So the forward path for that would be simply just be simply as 1 because there's no block there. Okay, that's forward path. Then we will look at this diagram again. You can find a closed loop there. That is what we see this. So arrow goes into K, arrow goes into G, and then arrow comes back to HS. HS goes into that summing block and then come back to the input of K. That is a closed loop. That's the only closed loop we can identify from that block diagram. Multiply every transfer function in the closed loop. It's called feedback transfer function, or the closed loop. The feedback transfer function in the feedback path. Okay, so there's forward path, there's a closed loop path or feedback path, there's forward path transfer function, there's feedback transfer function. Okay, they are different depending on what we are talking about. Now we are ready to find the transfer function of the overall system. Now, transfer function is between 2 signals. It's a ratio between the Laplace transform of one signal and the Laplace transform of another. Now, previously we only looked at the Laplace transform of the output and Laplace transform of input only because we were not looking at a closed loop. Okay, we were looking at a single block, so there is really only one input and one output. For closed loop, we have different choices. But for time being, say I want to define the relationship between RS, the overall input, and YS, the overall output. Okay. Say that's what we want to do. Say as our step number 1. Now to do this, first of all, I need to establish the input out and output relationship of each individual block. So for the plant GS, its input US times GS equals to YS. That's my equation number 1. For the controller, input is ES, the output is US. So it will be US equals to KS times ES. That's my equation number 2. For the feedback sensor, input to that block is YS. So it will be YS times HS equals to the output MS. That's my equation number 4. Okay, and then I have this summing block. It's a negative feedback, therefore it's RS minus MS equal to ES. So to derive the overall transfer function, this is the first step you need to do. You need to establish the relationship between the input and output of each block. Okay, write all equations down. Write all the equations down, including the one for the summing block. Okay, then I'm going to copy all 4 of that to the next slide so we can work on it. Step number 1. I'm going to substitute equation number 4 into equation number 3. Okay, because M equals to H times Y. Okay, now the purpose of that is to try to eliminate MS from the equations. Okay, so substitute M equal to H times Y into here. That becomes ES equals to RS minus H times Y, which is my equation number 5. Okay, now what I get here, now I can see I have an ES here. I can substitute this equation, number 5, into number 2 to get rid of ES. Okay, so this entire equation on the right-hand side of equation 5 is substituted into equation 2 to replace that ES. This will end up with a US equals to KS times bracket everything on the right-hand side of equation 5. That's R minus H times Y. After that, I can substitute U, the equation number 6, into equation number 1 to get rid of US. So YS equal to GS times US. US is equal to everything on the right-hand side of equation 6. So I'm going to put that into a bracket and put everything in there. Okay. The whole exercise, because we are looking for a transfer function between the overall input R and the overall output Y. So we try to get rid of all the intermediate signals, like a U, like a E, like a M. Okay, so that once you get to equation number 7, now if you look at equation number 7, there are only 2 signals exist here. One is RS, the other one is RS. So output YS, input RS, and output YS. The rest of that equation contains just transfer functions. Okay, so you only need 2 signals there. The 2 signals that you want to find the relationship between them for. And the rest is actually fairly straightforward. What I need to do is just make some reorganization. So I got that, I copied that from previous slide, and then I'm going to expand the terms on the right-hand side Okay, so ks multiplied into that smaller bracket, that becomes k times r minus k times hs times yf, which is what I have here. Again, and then I can multiply gs into the brackets as well. So that becomes g times k times r for the first term, g times k times hs times y, that is my second term. Okay, you just expand the terms into the brackets. Make sure you don't miss anything there. Now, we end up with equation number 9. And then what we do, we're going to reorganize equation number 9. We're going to put all the terms related to the output to the left-hand side of the equation. We're going to leave any terms that relate to the input RS on the right-hand side. So all I need to do is really basically move this term onto the left in this case. So negative becomes positive. So it's y plus g times k times h times y equals g k r. Next step is to look at the left-hand side, because I have two terms here, but there is a common term ys here and ys here. So I'm going to take this out of the bracket. So inside the bracket, it becomes 1 plus gkh outside times ys equals to right-hand side. I'm not really changing anything. The only thing I've changed is put a bracket there, but it didn't really change the mathematics. Okay, so it's g times k times r. The only reason I'm doing it is so I separate the transfer functions from signals. Once you get there, all you need to do now is to divide the coefficient, what's in the bracket on the left-hand side to both sides. Okay, if I divide this to the left-hand side, this cancels this out. So on the left-hand side, I end up with ys. Divide this by what's in the bracket, so that it becomes g times k over 1 plus g times k times h. Okay? So y equals to this divided by that. Okay? This middle bit is my transfer function. So I end up with the transfer function ps for the closed loop equals to ys over rs. That's my input. This is my overall output. That equals to k times g over 1 plus k times g times h. That's really the generic method to derive the transfer function of a closed loop system. Okay, so you don't really need to remember anything. You don't need to memorize anything. The only thing you need to know is for any single block of a subsystem, the Laplace transform of the output equals to transfer function times the Laplace transform of the input. And then you write down all relationships between each of the individual blocks, and then try to use substitution to remove the signals we don't want, and you end up with one equation, and then find the relationship between the output and input. There is, of course, a shortcut to it. That's my method number 2, and it's quite easy to remember. Remember previously I was trying to find the forward pass transfer function and feedback pass transfer function. Now this will come to use in the second method. To find the closed loop transfer function between any two signals. In this case, I have y over r. So input is r, output is y. Now, first thing we need to do is to find the transfer function in the forward path. Okay, so forward path consists of r going through the summing block, going through k, going through g, and then you get to ys. So there are really two blocks there. So identify every single block in the forward pass, multiply them together. You put that in the numerator. That's my k times g. In the denominator, we need to find the closed loop, the feedback pass transfer function. Feedback loop we have here is that closed loop. We have three terms there. There's k, there's g, there's h. Multiply all terms in the feedback loop. Stick that to the bottom and then plus 1. Okay? It's like a default value. So it's 1 plus the product of all terms or all the transfer function in the feedback loop. That will give you the transfer function from R to Y. So for the same system, for this system, if I have two other signals where I want to find the relationship between the input and output, the denominator term will always be the same because we only have one feedback loop. But numerator changes according to whatever input output we have. For example, if I want to find a relationship between R and ES, ES is my control error as a kind of output, because sometimes we want to examine what the control error is. The input is RS. Then the denominator term will be the same. It's 1 plus KGH because the feedback loop doesn't change. But the feed forward between R and E does not have any transfer functions. So on the top will be just simply a 1. Okay, so just to summarize for the method number 2, in the denominator you find the feedback loop transfer function, everything in the feedback loop. You multiply them together, then you plus 1. That's your denominator's done. In the numerator, you look at what is the transfer function you try to look for. You identify the forward pass from the input. At the bottom here is the input. The top is the output. Between input and output, find all the transfer functions, multiply them together, stick that to the numerator. So you end up with the transfer function. I'm going to run an example here. Now in this system, I have 3 different subsystems. I have the plant GS, which equals to 20 over S minus 4. I have the controller 1 plus 2 over S, which is a PI control. And I have a HS, which represents the dynamics of sensor. In this case, equals to 1. So it's a unit feedback system. Now, if you look at the individual subsystems here, for the open loop, I have a pole of positive 4. Now, to find the pole, remember, we need to equate the denominator terms to 0 and then find the solution of S, which gives us a 4. Because the 4 is a positive number, positive poles give us unstable systems. We have a DC gain of 5 or minus 5. Now, to find the DC gain, you just set S, every single S in a transfer function of 0. So 20 over minus 4, which gives me minus 5. We got no zeros because we can't equate the numerator term to 0. So this open loop does not have a 0, but it has a DC gain of minus 5. It has a pole of positive 4, and it represents an unstable system. For the controller, I'm going to reorganize that transfer function a little bit, so it makes life a bit easier later on. So multiply 1 by S over S, so that becomes S plus 2 over S. I have 2 parts of the requirements here. Requirement number 1 is to find the transfer function between the overall input and the overall output ys, i.e. I want to find the ratio between ys and rs. Part number 2, I want to find the transfer function from r to e. E is my control arrow. In other words, I want to find the transfer function between es and r, or the ratio of e and r, e over r. Okay, so first thing first, let's see what I have here for the first part. And because I want to find our transfer function between r and y, so I'm going to look for the feedback loop first. So in this case, there's a feedback loop here. And how many terms do we have here? In the feedback loop, we have 3 terms, k, g, going through h, and it comes back. So that's a feedback loop. So I'm going to multiply k to g to h, stick that to the bottom, plus 1. And then we're going to look at a numerator. What should be in the numerator? Because I'm looking for the transfer function between r and y. So I'm going to look for the forward pass between r and y. So from r, feeds through here, there's k, that's the first block. It feeds through again, that's a g, that's my second block. Okay, and then goes to ys. So there are only 2 blocks in the forward pass between r and y. So I'm going to multiply these 2 together, stick that to the numerator. Now, of course, that's the only expression. I have these g, k, h all transfer functions for the individual blocks. So I need to substitute g, k, h into here. That will give me g, k, 1 plus g 20 over s plus 4 times k, that's s plus 2 over s, times 1, that's hs. And of course, again, that's not end of it, because this looks quite complex. And then we have fractions inside of fractions, which is not what we want. So we need to try to get rid of that. So that's what my next slide will show. Okay, I'm going to try to get rid of the fractions inside of fractions. If you examine this, you will find the only thing I have to get rid of is this s minus 4. In the denominator is the same, s minus 4. There I don't have fractions inside fractions anymore. So to get rid of them, I'm going to multiply s times s minus 4 to the top, and also multiply s and s minus 4 to the bottom. This is same term over same term, so that's a 1. So effectively, I have not changed anything. So on the top, this s cancel that s out. This s minus 4 cancel that s minus 4 out. So on the top, the only thing I got left would be 20 times s plus 2 brackets. So 20 times s equals 20s. 20 times 2 equals 40. At the bottom, I need to multiply this with 1 first. Okay, that will give me s squared minus 4s. And then multiply this s times s minus 4 into here. This s cancels that s out. This s minus 4 cancels that s minus 4 out. So I got 20s, and 20 times 2 is 40 left. So I end up with a transfer function like that, because I can merge these two terms together. That'll give me a positive 14. Now this is a transfer function between y and r. Equate the numerator terms to 0. 20s plus 40 equals to 0. The solution of that will give me the 0 of the system, which is minus 2. Equate the denominator terms, s squared plus 16s plus 40. If you solve that quadratic equation, I end up with a minus 8 plus minus j2 square root 6. Now this is the imaginary part, this is the real part. The real part is negative. Therefore, the system becomes stable for the closed loop. The next thing you can examine is the DC gain. Now to find the DC gain of that system is quite straightforward. You equate all the s's to 0. So this term disappears, this term disappears, and this term disappears. So it becomes 40 over 40. 40 over 40, that's 1. So I have DC gain 1. That means output will equal ys or yt will equal to r, the input, in a steady state. So overall output will equal to overall input. Therefore, there is no steady state error. Second part of that example is to look for the transfer function between the input and the control error E. So we're looking for ES over RS. Now the denominator term will be the same as before because we only have a one closed loop. Therefore it's 1 plus K times G times H. That's in the denominator. In the numerator, we don't have anything between R and E. There is no blocks. There is no transfer function between them. So therefore it's a 1. So I'm going to stick at 1. And then I'm going to substitute G, K, H into this part, and which end up with this. Again, I need to simplify that fraction. So I'm using the same approach. I'm going to multiply s and s minus 4 to the numerator and s minus 4 to the denominator. So end up with, on the numerator, it's 1 times this. So that will give me s squared minus 4s. In the denominator, it's this term times 1, which will give me s squared minus 4s. And then that s cancel that s out. This s minus 4 cancel that s minus 4. So I'll end up with, I don't know where this 10 comes from. That 10 should be there, should not be there, so it's s plus 2. So that becomes 20s plus 40. That's the transfer function between the control error and the input. Now if you examine the zeros, now I have zeros. So if I equate the numerator term to 0, I have two solutions. I have two zeros. One is s equal to 0, the other one is s equal to 4. The poles will be the same because it's the same pole as before. Okay, so if we equate the denominator terms to 0, then I found the same poles as the previous transfer function. It is minus 4 plus minus j2 over times square root 6. Again, the negative part is negative. The real part of the character pole is negative. Therefore, system is stable. Now, if you look at the DC gain of this, again, find the DC gain, you equate all the s's to 0. So this term disappears, this term disappears, this term becomes 0, this term becomes 0. So your DC gain will be 0. What does that mean to a system behavior? It means in steady state, the control gain will be 0. Whatever, when you have an input, RS, which is good, which is what we're looking for. It's the same thing as the output equal to input in steady state, because then there's no difference between the two, therefore the error is 0. So they are really just confirming what we got here. Okay, I've got a few questions for you to practice. So the first part of that practice is I have a closed loop system here. GS equals to this, KS equals to that, and HS equals to 1. I want you to find the transfer function between Y and R. That's overall output Y, the overall input R. And then I want you to compare the open loop pole with closed loop pole, and also compare their DC gains as well, and make some observations about what these DC gains mean to the closed loop system, or to the response in steady state. And then second part, I have two questions for you. It's a slightly different system because we have another block in the output. Okay, all the transfer functions are defined, but this time I want you to find the transfer function of the closed loop between input and output wires. But also the second part is to find the transfer function between R and ES. Okay, thank you.